Hi, so the point of today's video is to clear up any confusion that there is about the three laws of motion that Newton did. So we're going to start off before we even go over any of those laws, talking about exactly what is a Newton. So a Newton is a unit of force. Whenever we talk about units, you're used to being in science class and hearing about things that you see in your daily life. When we talk about temperature, you understand because you talk about temperature just all the time in your daily life about what it's like outside. When we talk about distance, you can see on a ruler what those things mean. It makes sense to your brain. Whenever we talk about force, we talk about newtons. Nobody shoves you and goes, ha ha, I just hit you with 5 newtons of force. That just doesn't happen. So it's just kind of something that isn't in your daily life. So I want to give you some concrete image about what 1 Newton is. So whenever we talk about the science definition of what a Newton is, it is the amount of force required to take 1 kilogram of mass and move it at 1 meter per second squared of acceleration. That's still nonsense to you. That in no way helps you. So here, as far as on Earth, what 1 Newton feels like is if you would take something that's approximately 100 grams, which is what this little brass weight is, and you would put it on your hand and have the force of the gravity on it, what you feel on your hand is around 1 Newton of force, just that feel of it sitting there on your hand pushing on you. Most of you do not have brass mass sets at your house. It's not something people give to kids as toys whenever they're little. So I have an example that I know you all know what it feels like. Around 100 grams is also your most beloved possession. Oh, look, your most prized possession. Look, oh, the self, it even glows when you pick it up. It's magical. So you put this in your hand and you feel the force of it pushing down on your hand. That is around 1 Newton. That force that your cell phone exerts on the palm of your hand as you hold it. So get out your cell phone. Go ahead. I'm letting you in class. Get out your cell phone. Do it. Yeah. Okay. Set out in your hand. Feel what that feels like. Okay. It's not a ton. It's not a ton of force. So whenever you're doing problems and you see that there's a collision and it's these giant force numbers and there's thousands of newtons and you're like, that can't be right. It can. Because whenever you have something that has a lot of mass or has a lot of acceleration, it's going to create a lot of force. And so you can have some really high Newton numbers that are up in the thousands in these problems. And it's not wrong. It was just a big force. Hopefully this helps to clear things up for you. Now let's move on to Newton's first law of motion. And that one states that an object at rest tends to stay at rest, and an object in motion tends to stay in motion unless acted upon by an outside unbalanced force. So this whole law is about balanced versus unbalanced forces. If you have an unbalanced force, it is something that will cause an acceleration, which means a change in direction or a change in speed. Here are some examples of Newton's first law of motion in action.
Okay, so whenever we talk about Newton's first law of motion, there are two parts to it. An object in motion wants to stay in motion, and an object at rest wants to stay at rest. It's that whole thing about inertia. An object wants to keep the motion that it has. So, we're going to look at one part of this. We'll see if it works. Ready? Okay, so the washer that was sitting on top of that card wanted to stay at rest. So even though I flicked the card, it stayed where it was until gravity acted upon it and it fell down into the cup. All right, so we're going to look at the other part of Newton's second law of motion, and that is that an object in motion wants to stay in motion. So we've got our little purple minion here. Makes great noises. And he is going out for a Sunday drive. Now, being one of the bad minions, he is not a rule follower, and he doesn't need a seatbelt, he thinks. So he's going to go out for his drive, act reckless because crazy, and we will see why seatbelts are important. Something we're going to talk about, okay? So here he comes. All right. So the car stopped when it hit the thing, but our guy, he kept on going because he had that force of inertia working with him.
Okay, so that means that we're ready to begin Newton's second law of motion, which states that acceleration of an object depends upon the force and mass. This one is that equation, force equals mass times acceleration. And here are some examples of how that looks in the real world.
So we're going to take a look now here at an example of Newton's second law of motion. And that law is that force equals mass times acceleration. So mass and acceleration are going to show you how big a force is on an object. So if I take our little fan car here and have it travel 1 meter with nothing inside it, all right, I'm going to start a timer and let him go. And in 8 seconds, he was able to go that meter. I'm going to bring our fan car back. And the only change I'm going to make this time is I'm going to put this tiny little 20-gram mass in here and turn the fan car back on. Whoop, without hitting myself in the hands. Oh. There we go. All right, and we're going to let him go. All right, and we're at 21 seconds to travel the same distance. And the fan, since it was the same for both of them, and the car was the same for both of them, so same wheels, it should be the same amount of friction, it was on the same surface, all the other variables were the same. The only thing that changed was the mass of the car. That should show you that whenever you have the same force going into a situation, that if the mass is higher, the acceleration will be less.
And for our third and final law of motion, we're going to look at for every action, there is an equal and opposite reaction. So for our third law of motion, we're going to look at our final video.
I'm going to take my balloon here, put it onto this piece of tape, if the tape wants to work for me. All right, there is going to be a force coming out the back of the balloon whenever I let go of the end here. And that should cause an equal and opposite reaction of the balloon shooting in the opposite direction.
Hopefully all of these video examples help to give clarity to Newton's 3 laws of motion for you and will help you in the future as you try to apply these laws to different situations.